Greetings, everyone, and welcome back to this last episode on the scalable modeling approach. Here we have Simo, the one who has proposed this approach to our system
Hello.
design, and myself, Jose. And yeah, let's jump into it. Let's start with a brief recap of what we have discussed over the previous episodes, and I think it's important to go over these key things that Simo has described at the beginning, setting us into the why, how, what, and how of system design. Can you go over that a little bit, Simo?
Yeah, sure. Yeah, so this will be the last episode of this mini series that is going through the whole scalable modeling approach from the discovering the why all the way to the implementation. So let's have a bit of recap. Um, let's zoom in here first. So far in this podcast, video podcast, we have had a 3 episodes where we have covered the scalable modeling approach. We started always go into why do we need scalable modeling, what is it and how, and this is the kind of the structure that we go through in multiple levels in these episodes. So in first episode, we first of course started from why scalable modeling is needed, what are the things that it's addressing, where should it be used and where not. And I think that the main place where it is to be used is when we are designing systems in a growth ready fashion, meaning that if these systems become successful, the system structures are accommodating the growth without still doing any over engineering in the beginning. And then we moved to what. So we did go through already in the first episode the things, the components of scalable modeling and how to use it. But actually the how part was left for episodes 2 and 3. So how to do scalable modeling, we split that into two different categories. We usually start from temporal modeling, create this model which is more like flowing in time, process-oriented way of looking into systems. And then episode 3, we had the spatial modeling, which is more like actually planning how to arrange the system state so that it can be scaled if the need comes. As a recap from this temporal and space, so we had this picture. So my definition of system is that this system is a set of processes that are evolving systems state. There can also be multiple states within one system. And in scalable modeling, we need to design the system so that the state can be distributed if the need comes. And the processes are time-based. They are relating to time. They are kind of happening in time, and therefore they are temporal. Whereas the state, it's of course evolving in time, but it's always on a moment of time. It's located into a specific point in space, in geological space, for example. So when systems are growing enough, they need to be distributed, and the states, the one single machine cannot run one system's all states. So we need to distribute the state into multiple places. So we also need to do spatial modeling for the systems to prepare them to the growth if and when it comes. And that kind of build the bridge to the components, the main components in the scalable modeling. So in traditional system design, the components are sent to some sort of business logic policies that are then either accepting or rejecting the commands and altering the state if accepted. And then we can query the state. But what the scalable modeling is proposing is that we need to add the fifth element into those components, which is the event. And the event is basically the one that the processes are producing that are evolving the state of the system. And the event unlocks also the evolvability of the business logic and distributability of the application, where the distribution is the path to scalability and resiliency. So that's a short recap, but then this last episode in this mini series, the number 4. So what is this about? We have already covered the why, what, and how on scalable modeling, but we haven't really covered yet the how part of the implementation. So the scalable modeling also builds on top of this why, what, how flow. And in the episodes 2 and 3, in the episode 2 specifically, we did discover the why. Why do we need this system to be built, this Christmas present wishes management system? So we discovered the why, the reasoning, so huge volume of wishes, and that the wishes are changing after they have been wished. So that may cause some waste, some gifts that are delivered to children who no longer want those. So we want to solve these wishes, the huge volume of wishes and the very manual style of collecting those wishes via elves. It's something that we want to make a bit more efficient. And that's basically in the nutshell, the why of this system. And then from the why, we move to create the conceptual model. The what does the problem space look like, and what should the solution space look like? And for this what part, we did also in the episode 2 create this very simple ubiquitous language that describes the terminology that is common for the domain experts, common to the Santa Claus, and something that the developers should also use and build the structured application on top of. So we have children, we have wishes, we have presents and the naughty list. And we created the temporal and spatial models to cover the landscape of the problem and problem space, and gradually evolving that into a solution space that is kind of handing us the keys for the last part, which is how we will implement this system in practice. And this how is the part that we will be discussing today. So we will be showing you the actual implementation. This is just one part of the code from the command handlers where we are handling the incoming wish command. And basically here we are using the ubiquitous language. So if the naughty wish, if it is naughty wish within the command, so if the gatekeeper has detected that the wish was naughty, it has marked the naughty wish true. And in that case, we will be rejecting the wish with the reason that it was a naughty wish. And we will be responding with 400 bad requests and with this text. But if it wasn't a naughty wish, we will accept the command and we will store wish approved event, create a new ID for this new wish, and yeah, this event will be persisted. Also, in the case if the wish is rejected, we will also persist a wish rejected event.
Let me interject here a little bit. So just to go before we go into this code, this if we can like enumerate these key things that we have already described. So we have in the why and the what we discussed about why we need this approach, right? Like why is it that not only why Santa needs to, why he wants to improve his way of handling the wish management, but also why is it that scalable model might be the right approach for his problem. Uh, and then on the what episode and through discussions that we had, we also discussed about what are the pieces that are needed to get this solution to be scalable. It can be now or in the near future. And as you mentioned, we already have defined this, or we discussed this idea of this fifth element, which is the events, and how important they are, not just as means of integration or as way to serve as a conduit to the whole system design, but also as a key part in the whole system. This idea that when we model any domain, or when we model or when we try to implement any solution, we need to take these events as key parts that describe and drive the behavior of what the system is trying to do. That's for the fifth element. I think the other part that it's also key in what you just described is this idea of ubiquitous language, this common language that allows us to clearly define a language that would allow us as developers and Santa as the domain expert to communicate. So I think those are key things that need to be mentioned before we go into this code, in-depth code, or rather the how we're going to implement this, or you have implemented this. So I was thinking, I remember there's this diagram that you created that when every time I look at it, for me, it is like it makes a scalable modeling make sense. If we can use that as a way to see from a bit afar the pieces that made scalable modeling and how like you implemented the solution. If we can look at it side by side, or rather like we can go into it and you can say, okay, this is where an event takes place and or a query takes place, and this is how I implemented this. Could you go over that now?
Yeah, definitely. And coming back to what you said about the events, it's also something that it's really worth highlighting in the implementation. I think that it's the most of what scalable modeling is about is kind of built on the idea of that event and the power of this event, that you can create a simple systems by adding the events there, and this event has the power to make this system to grow when the need comes. So this is the kind of something that I hope that this webinar series will clarify to the watchers that how powerful is the concept of an event for growth readiness and evolvability. But yeah, let's start going through or getting closer to the code. I will just still do a recap of the previous things that we did do in the previous episode. So in the episode 2, we created this temporal model. So there's a timeline going, and child is basically first making a wish. Wish is received. We will check that the wish doesn't contain a naughty keywords, and the child is not on a naughty list. And also has this policy that the child can have maximum of 10 wishes. And if these policies don't kind of trigger, we will approve the wish, and then the present logistics will take over. It will in some point tell that now the present has been delivered, and we will mark the wish fulfilled. So this is the total process from child making a wish to the wish to get fulfilled. And there was an additional swim lane also, that we want the child to provide the child with the possibility to cancel the wish if the child doesn't want the present anymore, to reduce the waste. And after second episode, we moved to the third episode, where we converted this temporal model into a spatial one, where we center the model around space, the states of the system. So we did change the arrangement and remove the timeline from the top. We still did some replication in here. So the external systems, the present logistics, you can find it from here and here, and the naughty children management from here and here. And by doing some duplicated sticky notes and markings to this diagram, we can make it easier to follow it. It also contains these same processes, but in different format. But the biggest value in this diagram is that this starts to be quite close of what the implementation structures will also be. Yes. So now let's move to the implementation. First of all, you can find from a GitHub the repository called Wish, and there is a Wish management. And it is a simple Scala application using just a native Scala tree. Why I did pick Scala tree in this time and not, for example, C# or Java was that it doesn't matter too much what is the language, and these scalable modeling end results are sometimes benefiting from using functional programming languages that you will get to know soon, because command handler, for example, it is a stateless function. All the policies, they are stateless functions. So functional languages fit here, but we can also use basically also the Java and C# are just fine as an implementation language. But yeah, this Scala implementation just adds two libraries, the Cask that enables me to create HTTP endpoints, and this Ubico, which is helping me to convert Scala classes to JSON and vice versa. And then I have also the test libraries where I use the behavioral test style that I will show. And the implementation structure on the high level contains three packages. I have app. It's the application that contains the kind of the runtime, very simple runtime for this implementation. And I have just quickly crafted that there so that it can run it. And the value of the scalable modeling implementation is that there is also this structure folder that defines the kind of a blueprint for the application. So it defines the base structures, the journals, and the message buses that the application will implement. And we can engineer the application layer to be faster and more distributed and so on when the need comes. But when we start working with this kind of a scalable model implementation, we don't need fancy frameworks. We just need a framework that runs the business logic, and we can improve that framework later on because the structure allows it. And in the middle, we have the domain logic. So the structure provides blueprint for the application and the structure for the domain logic. And the structure is kind of the key of guardrailing the domain logic to be implemented so that it is growth ready, and it also guardrails the application or gives the structure to the application, kind of structure that doesn't prevent building a faster and faster application runtimes when the need comes, or taking already existing frameworks that can be matched to the need. So this is in the middle here, we have the spatial model with explicit policies added. Usually we don't need to add these policies explicitly when we are drawing these diagrams, and the scalable modeling, the blueprint, the first picture that you saw in the beginning, kind of tells that if there is a command, there always needs to be a command handler. If there's an event, there needs to be an event handler, and so on. So we don't need to explicitly add these, but it's good to, in this demo, to have these explicitly, because these are the things that we will be implementing. And if we quickly go through each of these three packages that we have and what they contain, we can find out that the domain logic, if we start from there, we can find that the domain logic, it contains these components. So we have event handlers, publish naughtiness. Basically, it's the naughty children management. For the naughty children management, it is this event handler here. So when the wish is rejected, if the reason for wish rejection was naughtiness, we will publish the naughtiness detected. So this is the event handler for that. And then we have publish wish updates. Well, we have two event handlers in the picture, but we can handle multiple events with a single event handler class. So we have publish wish updates, which is accommodating both of these event handlers. Then we have the gatekeeper. It's called a verify wish, and it is here. And then we have projections. We have the child here. We have the naughty list there. The naughty wish keywords, it's a special projection that we have hard coded for this demo to make it make the implementation faster. It's basically just a list of naughty keywords that we will map in the gatekeeper, and I directly hard coded that to the gatekeeper. If later on we want to make it dynamic, it shouldn't be a problem, but now it's hard coded there. Then we have a child, and this child, I'm using this kind of entity style here to map the functionalities, map the business logic. We could also use, for example, vertical slice architecture, where we would have packages for each functionality. But I decided, as this is still a relatively simple application, to use the entity style. So I have child entity. It's just an object, Scala object, stateless Scala object with stateless functions, and it contains the command handlers for the child. Then we have listed the private events and the public events in these classes. And the last one, we have stream. And this is a special thing in this implementation. A scalable modeling doesn't necessarily require it. You can basically choose what sort of a journal persistency model you use. But I have decided to use a creation of journal streams when these events are stored. So for example, when wish is approved, we are storing this wish approved event into multiple streams in the journal. So the child's stream gets this event, the wishes stream gets the event, and we can store this into multiple streams immediately during storage, because events are immutable, so we can make copies of them easily. That's one of the powerful features of events. So streams define into where we store the events, and that the streams define from where do we fetch those events later on when we, for example, create projections or handle the events for publishing them to outside, or to handling the event for updating a database. Or there can be multiple reasons, but it's for the stream. Stream is for event projection and processing. And then last thing here is the topic. So we have a message bus implementation to collaborate with external systems, and the topic is the message bus has topics where we can publish these public events. So it defines what topics are available in this implementation. And then to the structure. So this is something that we can reuse in our implementations. I have to say that this is the first draft of the structure. There is still room for improvement, but it has the basic elements there already. So we have, for example, traits for the policies. We have command handler, event handler, and gatekeeper. We don't have query handler here, but we can later on go and see from the code what is the reason. It's basically the reason is that it's very easy to do queries. We can do that already on the HTTP layer. When the request comes in, we can directly map it to a database or create a or kind of rehydrate a projection and return it. So there doesn't need to be explicit query handler because they are very easy, simple, traditional functionalities to fetch something from a system. In addition to these policies, we have the command and the private event here. We don't have the public event as explicit because they also they are defined within the application itself. There's nothing specific in the public events. Then we have a state, which is the base class base trait for all the states, and we have a specific state projection, which is the event sourced state type. Yes, so the structure defines these, and the event bus and the journal are something, the structure or blueprint for the application layer, the runtime. So that is a bridge to the app last package, and in this package we have the app, which is a place where we connect the pieces together. There is a thing called reactor. It's also started by the app, and it basically goes through the event streams and checks when the new events appear there. It will trigger the event handlers that are related to these events, and it kind of makes these asynchronous processes flow. HTTP app is taking the application and connecting it to the HTTP interfaces, basically connecting the commands and the queries to the application. And then we have in-memory implementations of event bus and journal. These could be easily be converted to something more persistent or something that you can find from the already existing solutions. So these are very simple interfaces that you need to implement. Yes, and maybe just one thing before jumping to the implementation is that the example implementation also is using the behavioral testing. And there's a lot of these test cases where we have this given when then structure in the test. So we have features with scenarios, and in those scenarios there is the given when then style used. So for example, in the first example, there is a feature about making wishes, and there's a scenario where child is banned because he or she has done a naughty wish before, and as the test says, given a child who is still banned because of naughty wishes, and we create a new normal wish, so non-naughty wish. When the child tries to make a wish, this normal wish, then no events are produced, and the command in response indicates that the child is banned. And we have these documents available also in the Git in every build, and also they get generated into the target folder of the application in development mode. All right, but this is the recap and the dive into the implementation. So, Jose, would you like to see something specifically from this implementation? And sorry, I think we can also have a bit of a sort of demo how it functions, because that also helps to understand how the system works. So I think we could jump to the demo in this point and then jump to code examples.
Sounds like a plan.
So this is easy to start. If you clone the repository, you go to the wish management folder, and if you have the SPT and Scala or the JVM installed, you can find also from the README the exact versions that you need to have. You can just do the SPT Scala build time run. And it will do a bit of building, compiling, and then it will start. Now it's running. And let's start by creating a wish. So let's create a wish. So this is now doing a HTTP post request to this URL. The child is Simo in this case, and we make a wish. The content is a knitted wool sock. And we got 200 OK back, saying that the wish went through. We could, for example, now use the query that we have. I will quickly show you. So what we basically now did, we made a wish. It did actually go through and check if the child was on the naughty list. It wasn't. It did check that if the woolen sock is naughty, which it wasn't. So it went to the command handler, which created a wish approved event, and it actually got even published to the present logistics. But then we can also do the query get child state, and this query will rehydrate the child state from the events and return it to the caller. So let's try that. And I will pipe this to the JQ to make the response to be pretty printed. So now we can see that there is a child Simo, and there is one wish with this wish ID, which is the knitted woolen sock. And let's make, for example, another wish just quickly and wish for a world peace. And if we now check the status, fetch the child's state again through the query, we can see the world peace there as well. And now we could also check, I have created interfaces, HTTP interfaces to see what, and also to subscribe to the present logistics and naughty children management. So let's check what kind of events have been published to the present logistics. So we have this events interface to a wish updates topic with an offset of 0. And we send it, and we can see that, okay, there are 2 events have been delivered to the present logistics. And we can use also this HTTP API to kind of poll these by storing the cursor. Now the cursor in the last event was 2. So if we would add 1 here, we get only the second one. If we add 2 here, we get empty list. But when the third event is published, then we would get it. So we would be able to this kind of pull-based, do this pull-based subscription. All right, but then what we could do is that we could, for example, make a naughty wish. So I'm wishing for a flamethrower. And what happens is that I get a 400. It's a very bad request. And it's basically denying the flamethrower from me. And if I'm now checking what is my state from the query, I'm noticing that hey, I've been banned until 1 minute for 1 minute time. So if I would now try to do some a non-naughty wish like flowers, it won't go through because I'm banned. And this banning is implemented in order to make the naughty children management to act in time so that it can basically process my naughty wish. So if we check from the what is in the pipeline going to the naughty children management, we can see that this one naughtiness detected public event has been now published to the naughty children management. And the naughty children management has a decision to be made. So it needs to decide that how long will we have this child to be added to the naughty list. And then I'm kind of simulating now the naughty children management here and calling our integration endpoint. I will show which one so that you can keep track. So I'm simulating this process here and I'm calling, this process here and I'm calling mark naughty, which is supposedly coming from the naughty children management. So the naughty children management makes a decision that the child is on a naughty list until Christmas. So let's send this through. And now if we check this child state again, wrong API. Here we can see that I'm on a naughty list until the Christmas is gone. So, and something else also happened. So there's no longer the wishes. So what happened here? We can check it from the, for example, by subscribing the present logistics. So present logistics, let's see what kind of messages were delivered there. So we can see that, okay, so these wishes have been cancelled. So what happened was that when I was added to the naughty list, the business logic did cancel all my previous wishes. And if we want to see that how is this persisted to the database, we can take a look to the interface that I've created that just takes in all the events from the journal from a stream called Simo Child and shows those. So these are all the events that are related to me now. So first the wish was approved, the second wish was approved, then I did the naughty wish. There was a reason it was rejected, it was naughty. Then I became naughty and I'm on a naughty list until the Christmas is gone. And there was an automation that cancelled all my existing wishes. And now if I would try to create a new wish, something, let's wish the world peace again. I'm a naughty child, so I cannot wish. So this is the logic in a nutshell. And the only thing that is persisted is the stream of events, or actually the streams of events. There is also, I can just quickly demonstrate to the end that if we check what journal streams exists, there is also, for example, this stream. And if I subscribe it, maybe I think I wrote it wrong. It's naughtiness. I can see that there was two events relating to naughtiness in the system. So I could create a projection from the base of these about the naughtiness status in the system, for example. And we can also stream these events to an additional systems real time. We can basically create copies of the persistence of this system, for example, by every now and then polling this system and storing the cursor value. So now I have the cursor value 2 here. And if I would put the offset to 2, I would not get any new events, but when the third event would be added to this stream, I would get it, and then I can store the cursor and refetch the new events and so forth. So these APIs can be used to stream out the events, make a backups, or create another versions, read versions of these systems or whatever. Yeah, I guess this is a demo how it's used. So you can also try it on your own machine, and there are also other things that you can do, like marking the wishes to be fulfilled, for example. Yeah, but now let's jump back here, and is there something that we would want to see in more details from the actual code?
Yeah, I was thinking, how is this policy? Like, how do you define these policies? And then also the gatekeeper is on the code.
Yeah, good question. Let's start from this gatekeeper and let's see how it has been implemented. So if we jump to the code, by the way, you can find from the README also these pictures and also the API course that I did, so, and the explanation of how the journal streams are implemented and how they can be fetched. So more info available there. But if we jump to the prod section, we can find all the business logic from the domain. And in this domain folder, as you remember, we have a policy folder, and we have a gatekeeper folder here, so we can open the verify wish. And if we check what it is about, it's extending a gatekeeper class. And if we check what gatekeeper is, it's a simple rate which implements or defines just one method handle that takes in a command, and it returns future of an effect. And the effect is the gatekeeper effect here. And it's basically just a case class containing either comment response or a command. So if it's returning comment response, we will return the comment response to the caller. But if it's returning a new command, we will pass on this command to the actual internal command handler. And if we check the structure of the verify wish, it goes so that when the handle method is called, we will first rehydrate the naughty list, which is one of our projections. It lists all the naughty children there is. It gives the rehydrate method, it gives the journal to it, so that rehydrate method can use the journal to fetch the events from the correct stream to rehydrate the projection of naughty children. And this projection we will map so that we can find if it contains children with the given child ID from the command. So basically, in our case, it would be checking if Simo is on the naughty list. And it will store the result here. And then we also will check if the wish is naughty. We will get the wish string from the command, and we will check if it's naughty. And this was the hard-coded thing that I mentioned. So the naughty wish keywords are here. And for example, the flamethrower is here on the first. So that's why it detected that my flamethrower wish was naughty. And when it has checked the naughty list existence and the naughty wish, it will add the results to the command that it will pass on in the gatekeeper effect. And maybe it's good to see also that what makes this gatekeeper to work. So I've done it so in here that in the HTTP app where we have make wish HTTP endpoint, it gets the child ID and it gets the wish. What it does, it's creating the gatekeeper, the verify wish gatekeeper. Here you can see that it extends the gatekeeper and it gives the child ID and the journal to it and calls handle make wish command with the wish. And then it takes out the effect and stores it here. And then what it does is that it checks if the gatekeeper's effect was command that should be passed on to the command handler, or if it was the command response that we would immediately want to respond back to the caller. And let's now assume that there wasn't anything that we should immediately respond back to the caller, so we will pass on this command to the command handler called make wish handler. And command handlers, they want as an input parameters, they want the current state that they validate the command against and the command. And to get the current state, we have fetched the projection child and rehydrated it with the journal. And then we are passing on that child's state to the command handler's handle method. And from here we will get the command handler effect, which is a bit similar, but with the difference that the command handler effect actually contains, and I get to see, it contains the events that are to be stored or empty list if nothing wants to be stored, and the response that is sent back to the caller of the command. So how it goes is that then the command handler will return the effect which may have the events that we will then append to the journal. So we store those events there. And we can also provide the cursor value because we get, when we rehydrate the child, we get the child's current version, which is the cursor. And when we are storing the new events back, we can use that cursor to enable optimistic locking so that if somebody is using this child in between these lines, we don't get into some sort of a conflict in the state. And then we will map the response back to the caller with the future successful command response. And that is the whole HTTP making a wish. And this is something that could be done also somewhere else, but it's something that can also be easily done on the HTTP level. I can just also now when we are here show the query and why there is no explicit classes for the query. So this is the get child state, and what it basically does is that it creates projection of child with given child ID and rehydrates it with the journal. So it basically does a fold left with the events of the child, and it gets the state of the child and the current version or cursor of the child. And it just responds with the state. So no need to do any query handlers because this is this simple to handle the queries. So basically, the command handler, the gatekeeper and the command handler, they were kind of orchestrated in the HTTP layer in this implementation.
Nice. And then do you show us the events? How do you define the events?
Yeah. The events, so we can see these 5 events here. So let's see how they have been defined. So jumping back to the code. The events can be found, they are part of the domain, and there is a list of private events. So, and this is the events are here. So we have a wish approved, which is a case class. It contains a wish ID, child ID, and the wish, and it extends child event. And it's also wish related, and it derives read writer so that we can convert this to JSON. So this actually the only ugliness in this domain package is that I needed to add these read writers here so that I can convert these classes to JSON. It's really hard to avoid, but that's the kind of the trade-off that I did in this implementation. And why this is child event and wish related is that relating to the fact that the wish approved is actually stored in the child's event stream and also the wish event stream. So if we check these, and the child event defines that there is a consistency stream where we should add this child event, which is called a child. And it also creates streams for each specific child. And there is a projection stream for wish-related events where it stores the same events as well. So I have, in this implementation, I have 2 types of streams. I have consistency streams where it is made sure that no one can write in between, that the consistency is preserved. So it's like a strong consistency boundary is applied when you are defining the consistency stream. But then you can also define these projection streams for events. And it means that these events are also stored into the projection streams, but there's no consistency, strong consistency involved. So they are just added to those streams. And if there are some intermediate events coming in between, that's totally fine. Meaning that basically there's no strong ordering in the projection streams, whereas in consistency streams there is. And one event can belong maximum of 2 consistency stream, but it can also belong to multiple projection streams. But this is a detail, something that I just experimented with in this implementation, not anything related strictly to the scalable modeling or CEQS, something that you can do. And it's kind of inspiration comes from the dynamic consistency boundaries that has some similarities with this approach. But yeah, but the events are defined in this private event object, and they are just case classes defining what there is, and they are deriving the read writer so that they can be encoded into JSON and stored in that format. Public events then are also described in here, so they are also just case classes, and they can also be encoded and decoded to JSON. So there's a bit of this ugly boilerplate from the Ubico that is just something that you just need to have to be able to convert this to JSON back. So basically, the gatekeepers, command handlers, and kind of these event handlers, they are defining the business logic. The state would also have objects that would have invariants in them. So type of this kind of aggregate type of objects that have some business rules in them. And when the command handler is applying or validating the entity, it can check those invariants in that point. This logic is relatively simple, so I didn't add any invariants to these states, but that is possible.
Thank you. I really like how in the code, like there's this just one repository or directory for the domain, and everything in there just extends from the structure and the app information there. Thank you so much for showing that.
Yeah, no problem. I think we actually covered pretty much everything, so it's not so complicated. And for example, this part here is actually not even needed. I just implemented it because I wanted to prove that the gatekeeper can do multiple queries in parallel and then collect the data and hand it over to the command handler. But actually, the child already knows if it's on a naughty list, so this would not be necessary in this implementation. So we could remove it and the system would still work as is. I don't know if there's anything else that we should present, but maybe as a kind of final thing to say is that now if this application would become successful, even though it is been running on a very simple runtime, we would of course need to put real persistence there before doing this in production. But in addition to that, we don't need to do any optimization upfront. So if this would become successful, there would be, and I supposedly there would be many children that would start using this. We would need to start scaling this. And the scaling this is very easy because we have all the command handlers that are defining the logic, the validation logic. We would have the invariants in these state things. We would have the logic in the gatekeepers, in the event handlers, and all of these are just stateless functions. The only state there is within these events, and these events are immutable, so we can make copies, we can create real-time streams from these to add another system. So hope you are able to see the possibilities that there exist to scale this system easily by creating more performant implementations, making copies of these logical pieces, adding them to this more performant runtime, and streaming those events there. That's very easy, and we can do these kind of migrations without any downtime. That's the power of events.
All right. I think there are no more questions on my end. So I think we can end this episode for now. Just want to thank you, Simo, for taking the time to go over this with me here. I learned a lot. I'll continue to learn. And yeah, anything you would like to say?
Yeah, likewise. Thank you for joining with me to this podcast mini series and making it possible. It was fun. And I guess there's nothing else to say that I hope that you will keep in contact if you find this interesting and we can together building this forward. This is in no means comprehensive and ready and perfect. So I'm always happy to hear any suggestions for improvements, any critiques as well, everything that helps me to learn more and create this forward. And I guess the last thing to say is that to wish you a happy holidays and behave.
Agree. Happy holidays. Thank you, everyone. Thank you, Simo.
See you. Bye bye.
Bye.